Welcome to the National Council of Supervisors of Mathematics, NCSM, Leadership in Mathematics podcast. NCSM is an organization supporting mathematics education leadership at the school, district, college, university, state, province, and national levels. Its membership constitutes an international force collaborating to achieve excellence in mathematics education. Be sure to visit the NCSM website at mathedleadership.org. Welcome to Episode 24 from the series of podcasts recorded at the NCSM annual meetings. This talk by Zalman Usiskin was recorded at the 2009 annual conference in Washington, D.C. The title of this talk is 4 Years from First Year Algebra to Calculus is Not Enough. Many of our best students take algebra in 8th grade and calculus in 12th grade. Because of their success, we expect other students to go from algebra to calculus in 4 years. Zal argues that this is an unrealistic expectation with a rich standards-based curriculum. Mr. Usiskin is introduced by Steve Victora, the Central 1 Regional Director. Be sure to tune in to future episodes of the NCSM Leadership in Mathematics podcasts.
My name is Steve Victora. I'm the Central 1 Regional Director on the NCSM board. And I have a question before I introduce Zal. Is there anyone here who has not heard of Zal Usiskin? So he's truly a man who needs no introduction. And I don't intend to read what's in the program book. I have that scripted. I have it scripted in large enough font that I can read it without my reading glasses. I just want to say a couple of other things about Zal very quickly. I know you're here to hear him. I've known Zal for 35 years as a friend, as a teacher, and my professional mentor. So it is indeed a pleasure for me to be able to introduce him today. Throughout all of his work, some of the highlights of which are mentioned in the program book, there are a couple of themes that are constant. One is that the student is at the center, and second, that the mathematics is good. And it's not stated in the program book, but Zal did start as a high school teacher in the Niles district in Illinois, suburban Chicago. In fact, is a product himself of the Chicago Public Schools. As a teacher, he has not only taught at the Niles schools, but when he began work on the University of Chicago School Mathematics project, he began writing in 1983. He would write, go to Glenbrook South High School in suburban Chicago, teach the materials that he just wrote, go home, revise, write some more, and continue. In 1983, he was developing a curriculum, a course for 7th graders that required scientific calculators. Another theme in Zal's career is that he's always been ahead of his time. Even in the 70s, if you look at some of his work, he wrote an algebra book through NCTM that was based on applications. In the early 70s, he wrote a geometry book based on transformations. I remember when I first met Zal as a graduate student in 1974, he gave me a copy of that geometry book, and I went home. I read it that night. It was beautiful, and I just enjoyed reading it so much. It's something that also had an influence on me. So he's done a little bit more than stated on in the program book. And yesterday, when I told him that I was in, he asked me if I was going to come to the talk, and I said, yes, I'm going to introduce you. I think he was a little worried that there were some stories that I might say, but then I realized he really has the last word.
Steve didn't mention that he is a gifted teacher and a gifted department chair. Steve Victora, we have known each other for over 3 decades, and he also taught my son, who survived him, taught him calculus. So we've known each other in many different ways. It's kind of hard, I must say, if you were at the opening session, to follow a session like that. There's no way that I could say that the issue that I'm going to talk about is as important as the issue that Katie talked about this morning. I mean, this is the internal kind of thing that we try to do to improve school mathematics, but it's not the same as the societal kind of thing that Katie was talking about. And to some extent, I wish I now had a different talk than the one, that would sort of follow up what she was saying and say, yes, and this is how to do it, and so on. If there's one message that might connect, and I assume many of you were how many of you were at the opening session? Yeah, you're almost all. That if there was one connection between that talk and this one, it is that the notion of starting children into the algebra sequence earlier, rather than sort of delaying them and waiting for them to be ready. If you wait for them to be ready, they will not become ready. Algebra is like a foreign language, and algebra needs to be started really quite early. I don't mean a formal course in algebra necessarily. In fact, I don't even mean it at all. But the language of algebra, the use of variables and so on, has to start early. And part of this is that when I'm talking about 4 years is not enough, I'm really not talking about adding years on the end of it. I'm really talking about if you start earlier, you can have that time. Well, now that I have departed from my script and I don't know how to get back into it, we'll just see. We'll see what happens in this talk. Over the centuries, mathematics has tended to be taught earlier and earlier, if at all. In the 1700s, Yale was the first university to require arithmetic for entrance, and Harvard had started in 1636. So you can see that there had been a long time where there was not. William and Mary had started in 1691. So it was the 1700s that you first required arithmetic for entrance. The first college requirement that students have algebra was in the early 1800s. The first requirement that students have geometry was after the Civil War. By the end of the 1800s, secondary schools in the U.S. were teaching a variety of mathematics courses. The difference between the course taking and course availability in high schools was diverse enough in mathematics and in other subjects that a committee was established in 1892 by the National Education Association to bring some order to this chaos. That committee, the Committee of 10, was chaired by Charles Eliot, the president of Harvard. Its report urged that the study of arithmetic be completed by the age of 13, and that the study of systematic algebra should be begun at the age of 14, and that the study of demonstrative geometry, that is, demonstrative geometry doesn't mean, it means geometry with proof, should begin at the end of the first year study of algebra and be carried on by the side of algebra, interesting, by the side of algebra for the next 2 years, occupying about 2.5 hours a week. Later that decade, a committee of the College Entrance Examination Board recommended 1 year of algebra and 1 year geometry be required of all students. And this, if you combine these two reports, this is how algebra and geometry became established as 9th and 10th grade subjects in our high schools. High schools that offered 4 years of mathematics followed that year of algebra by courses called intermediate algebra and college algebra, taking a year to a year and a half. The year of plain geometry was followed by a study of solid geometry and trigonometry, typically 1 semester courses, each with their own book. After these courses, a student who studied more mathematics would take analytic geometry and then calculus. Analytic geometry was where you studied graphing in detail with various forms of equations of lines, slope, intercept form that we don't teach much today, point slope, and so on. The conic sections, polar coordinates, equations for famous curves. This was analytic geometry. Thus, there were from 4 to 5 years between algebra and calculus. The course names intermediate algebra and college algebra still remain today, particularly in 2-year colleges. The course names tell you their origins. College algebra was a course that was historically taught in college. Intermediate algebra was a course sometimes taken in college, sometimes taken in high school. This was the situation when I entered the University of Illinois 50 years ago this fall, at the age of -4. You were not expected to have studied any calculus. If you wanted to be an engineer, and the University of Illinois was very strong in engineering then as it is now, you took analytic geometry your first semester, and then for the first half year of calculus your second semester, and you finished the year of calculus in the first semester of the sophomore year. If you wanted to teach mathematics, and there was a different major sort of for mathematics teaching as for mathematics, then you were expected to begin calculus in your second year, in your sophomore year. In fact, the program of studies for the freshman year allowed for students to want to teach who had only had 2 years of high school mathematics. The deficits would be erased by taking courses in algebra, college algebra, trig, and analytic geometry, and passing a test, no course, passing a test in solid geometry. Even if you were a mathematics major, as I was, you were not expected to take calculus in your freshman year. You took college algebra or trigonometry your first semester, analytic geometry your second semester. Then you began calculus in your sophomore year. This was the standard program. I turned out to begin it in my freshman year at the age of -4, as I mentioned. The University of Illinois was not atypical. In fact, it was then as now the flagship university of the state. Anyone who thinks that students in the United States today are not as well prepared as the students of 50 years ago is living in a dream world. And of course, there are many fewer students being prepared than there are now. So the first summary point is that 50 years ago, most curricula took 4.5 to 5 years to proceed from algebra to calculus. And of course, that's was if you succeeded. If you actually made it through the courses. The situation in school mathematics changed significantly in the nation around this time, around 50 years ago. In 1955, the College Board instituted its advanced placement program. And one of the AP courses from the very beginning was calculus. There were not two courses, there was just one called calculus. A small number of schools had been teaching calculus to their seniors, often by squeezing the 4 years of algebra, plane geometry, intermediate algebra, college algebra, trig, and solid geometry into 3 years, and teaching analytic geometry as needed along with the calculus. An increasing number of high schools began offering AP calculus, and as they did, they realized that squeezing all of the stuff into 3 years was not easy even for good students. And so in the 1960s, and then well into the 70s, 8th grade algebra began to be offered as a first course in the preparation of students for AP calculus. That was the reason. The new math curricula were a great help in this process because they streamlined the high school curriculum in order to make calculus a freshman course. Solid geometry was integrated with plane geometry. Trigonometry was put into the intermediate algebra course, which came to be called Algebra 2 with Trigonometry. Those of you know the books, you know the titles of these books. College algebra and some of the other prerequisites for calculus were placed in a senior course that had a variety of names, including Introduction to Analysis, Elementary Functions, Pre-Calculus Mathematics. Analytic geometry is no longer a separate course. Calculus books became called Calculus with Analytic Geometry. I might note that you couldn't just increase the demands these courses placed on students simply by fiat. You had to do some work earlier. For the first time, books for 7th and 8th graders came to have significant amounts of algebra and geometry in them. Pre-algebra courses had even more algebra than the basal texts, but they sacrificed some geometry to do that. So starting in the 1960s, we had today's modal curriculum: a year of algebra, a year of geometry, a year of second-year algebra, and a pre-calculus year, and then calculus. 4 years from algebra to calculus. You were considered accelerated if you took first-year algebra in 8th grade, and behind if you took first-year algebra in 10th grade. That's how it's in our minds, it's situated as a 9th grade course. You're considered accelerated if you take calculus in the high school, and if you have to do something in college before you take calculus, it's remedial. Or in our minds, they are 9th and 12th grade courses. I don't have data on the percent of students who were taking algebra in 8th grade during the 60s or 70s. The earliest data I could find comes from the Second International Math Study, which took place in 81-82. It's SIMS. And this is the first of a slide. You'll see the rest of this slide later on. 13% of the randomly chosen courses in the study of 248 randomly chosen classes in 8th grade in the study of Sims were considered to be algebra classes. How did these students do? By coincidence, the 8th graders of 81-82 were in the entering college class of 1986. And we do have at least one study of what happened to them in one state at one university. Bert Waits and Frank DeManna, well known to NCSM people, were in charge of the mathematics placement test for freshmen into math courses at Ohio State. As a state, Ohio typically scores higher on national assessment than the US mean. And at the time, Ohio State was required to accept all students who wish to go to it. Is that still true? Is anybody from Ohio here? They still have to accept everybody? No, they don't. Okay, but they had to at that time. Grades on the placement test ranged from 1 to 5, with a grade of 1, that's at the left, meaning that you got into calculus, or you're ready for calculus, grade of 2 or 3, meaning that the student was deemed ready for 1 or 2 semesters of pre-calculus, and a grade of 4 or 5 called remedial. And here's the grade distribution of showing it on the placement test for the entering freshman class of 1986, based on the number of years of college prep mathematics the student had. The article from which this graph is copied is called, "Is 3 Years Enough?" All right, is 3 years enough? And on the graph, the legend at the bottom tells you that the white bars stand for those students who had 4 or more years. So if you look at just the white bars going across, what you have, those percents should add to 100% on the white bars. And the checkerboards are the students who had 4 years only. If you add the checkerboards, you should get 100%. Do you see how that goes? And these are their scores on the placement test. Of the students who had exactly 4 years of college prep high school math, 7% scored 1 and therefore were considered ready for calculus. Of those who had 4 years. 31% scored 2. You see, that's the highest of the white. I'm sorry, that's the highest of the checkerboard. Just the ones who had 4 years, the checkerboard. 44% scored 3. That's the highest for the checkerboard. 10% scored 4, and 8% scored 5. Well, only 7% of those students who had 4 years of high school, college preparatory high school mathematics got into calculus in 1986. I think 7% is fairly low. I think they should have titled the article, "Is 4 years enough?" Do you see? I mean, their data really tells them 4 years is not enough. However, we have to probe a little farther when the results are so negative. Why are so few? It turns out this test was very difficult. Only about 28% of the students with 5 or more years were considered ready for calculus. That's the white ones. Only 28% of them. So, and they had calculus. That's what 5 or more years. So the calculus students weren't considered ready for calculus. So let's be a little kind, and let's say if you got a score of 1 or 2, you were ready for calculus. Now 38% of the students with exactly 4 years of high school college prep mathematics would have been ready, but 62% would not. Again, I think you could say 4 years was not enough for the majority. And I don't think Ohio State's placement test was unusual or would be considered out of the ordinary these days. It was heavily computational and could not have taken advantage of graphing calculator technology because graphing calculators had not come in yet. Over 20 years later, there are still mathematics departments wallowing in the dark ages and not allowing graphing technology on their placement tests. What is interesting is that this study was done before graphing calculators, so the ostensibly poor performance of students on such a test cannot be blamed on graphing calculators. Today, we speak of the mismatch between what's taught in high school and what's on college placement tests, and some mathematicians blame the use of technology for the poor scores. This study shows that the problem of students ostensibly not being prepared for calculus, even with 4 years of high school mathematics, was present quite a while ago. Nevertheless, if we use a college mathematics department's view of whether 4 years of high school mathematics is enough to prepare a student for calculus, these data would have us conclude 4 years beginning with algebra is not enough. That reason lurking behind the scenes in the 1980s surfaced even greater with the NCTM standards of 1989. The curriculum and evaluation standards recognized what last year's National Mathematics Advisory Panel did not, and that is that the purpose of school mathematics was not just to prepare students for calculus, but also to teach students the statistics and discrete mathematics they might need for majors in business and the social sciences, and to teach students how to use technology and mathematics in their everyday lives. A curriculum for all students must be a curriculum in the mathematical sciences, not just in mathematics. And it has to be a curriculum designed to make mathematics meaningful in life outside the math classroom. And so in the NCTM standards, in the curriculum evaluation standards, there were quite a number of topics that were not in the traditional algebra to calculus sequence that were considered important that students should know if they're going to college. Bear with me. They were expected to know under the number and operations standard, they were expected to understand vectors and matrices of systems that have some of the properties of the real number system. Under the algebra standard, they were expected to understand and perform transformations, such as arithmetically combining, composing, and inverting commonly used functions, using technology to perform such operations on more complicated symbolic expressions, use a variety of symbolic representations, including recursive and parametric equations for functions of relation, judge the meaning, utility, and reasonableness of the results of symbol manipulations, including those carried out by technology, use mathematical models to represent and understand quantitative relationships. Under the geometry standard, to understand, well, I can keep going. It's not just one topic. It's not just one day. These are big things. I mean, you'll understand, represent translations, reflections, rotate, dilations, yeah, by using sketches, coordinates, vectors, functions, notation, and matrices. What are you going to do Tuesday? I mean, this is a quarter of a year? I mean, how much is this? This is more than a chapter. This is more than even maybe 2 chapters. This is a lot of stuff. Use various representation, use vertex edge graphs to model and solve problems. Okay, vertex edge graphs we can do in 2 or 3 days. Geometric ideas to solve problems in, gain insights into, in other disciplines and other areas such as art and architecture. Oh, we can sneak those in, right? Understand? Okay. Under an entire standard devoted to data analysis and probability, an entire standard that didn't exist in the traditional algebra to calculus sequence, there was. To understand differences among various kinds of studies, in types of inferences, know the characteristics of well-designed studies, understand the meaning of measurement data and categorical data, of univariate and bivariate data, of the term variable, understand histogram. You know, what's interesting about this is that just a few years ago, the American Statistical Association came out with its GAZE standards, guidelines for the assessment, instruction, and statistics education. It's very similar to these things. It is not more extensive or less extensive. It's very similar, and it goes on. Compute basic statistics, understand the distinction between a statistic and a parameter. For univariate measurement data, to be able to do certain things. For bivariate measurement data, display and discuss bivariate data, recognize how transformations of data affect shape, center, and spread, identify trends in bivariate data, find functions that model. And what do you do Wednesday? I mean, this is, again, not something you do in a day. This is a full course. This is not just, I wasn't done. Use simulations to explore the variability of sample statistics from a known population. Understand how sample statistics reflect the value of population parameters. Evaluate published reports that are based on data. Yes, let's evaluate the NMAP in our statistics. The National Math Advisory Panel report based in our statistics classes. No. Understand how basic statistical techniques are used to monitor process characteristics in the workplace. Oh, there's more. Well, you get the idea. Probability distributions, random variables, conditional probability independent events, compound events. I believe that's it. Just 7 slides. Where was the time for all this to be found? Not in streamlining classroom procedures. In fact, the standards promoted communication, discourse, activities, and a general classroom atmosphere that discouraged lecture. You couldn't just teach it by saying, okay, students,
Today we're going to understand the concepts of sample space and probability distribution. I don't have time to really go explain these things, but I'm going to lecture them to you and construct sample spaces distributions in simple cases. Here is the sample space. Here is the probability distribution. Got it? Go home and think about it. A page in the 1989 Curriculum and Evaluation Standards told of topics that should be de-emphasized. 1 page. The general view was that so much time was spent on complicated manipulative skills that a de-emphasis there, not a removal, but a de-emphasis there would give you months to do other things, and the use of technology would make a lot of mathematics more efficient. But we learned very quickly that when we had powerful technology, we wanted to use it to do things we couldn't do without the technology. And we learned that we could not save time because we spent more time discussing graphs than ever before, because graphs tell us so much about functions and their behavior. With geometry software, able quickly to draw figures and see their properties, but we've learned it takes time to use the technology. And when you've got the technology, why not use it to discover things that were beyond what was in the standard textbook? So technology has not shortened the amount of time we spend on topics, but changed our approaches to them. It also takes time to learn and discuss the applications of mathematics. Sometimes these applications replace the traditional word problems, but at other times they were new content. This, too, takes time. So we learned that a curriculum that prepares students for the mathematics they will encounter in college and life takes more time than the traditional algebra to calculus curriculum. Allow me to say a few words to plug the project with which I've been involved for 26 years, the University of Chicago School Mathematics Project. UCSMP's broad outline for grades 7 through 12 was basically set 25 years ago, by the end of 1984, 5 years before the NCTM standards. Known to us at that time were 3 points that I've made so far. That 4 years was not enough to do what we wanted to do, that historically it took more than 4 years to get from algebra to calculus, and that students with only 4 years of high school mathematics usually don't get into calculus. And a curriculum that teaches the mathematical sciences was known to us that would include both pure and applied mathematics would take longer. Furthermore, we had examined the 7th and 8th grade textbooks in the United States and other countries. We learned 2 things from this. First, the US basal 8th grade math textbooks were very much like their corresponding 7th grade. This is because you had to do enough in the 7th grade to get some of those students into algebra in the 8th grade. So you covered everything by the end of 7th grade, and then 8th grade became sort of a remedial course for the students who didn't get into algebra in the 8th grade, despite the fact that at the time only maybe 15% or so were getting into algebra. A study by Jim Flanders, then at the University of Chicago, then a graduate student, confirmed this, showing, and let's see if we can understand this, showing that only 30% of the pages in grade 6, which is in blue, in grade 7, which is in red, in grade 8, which is in yellow, that only 30% of the pages of the 3 best-selling books, that's the yellow, take the average of the yellow bars, had any material, the bestsellers were Holt, Addison Wesley, and Scott Forsman at the time. That only 30% of the pages had any material on them that hadn't been covered in previous years. Second, the curricula of many foreign countries covered much of the algebra and geometry that we would study in 9th and 10th grade. So we had this sort of gap in the US curriculum. 8th grade was a vacuum. I might say that Jim Flanders had his study went from kindergarten through 9th grade, and he also found out that 2nd grade was a vacuum, which was the big surprise. We already knew about 8th grade. He was just confirming things. The surprise was nothing new was being taught at 2nd grade. So he had room both at the bottom and sort of at the top of the K-8 spectrum. Notice that 6th and 7th grade don't have that much new material either. On the average, 6th grade has only 38%. That's the blue, that's this, let's see, right here, 38% on the average of the 3 series had anything new, and 36% of 7th grade texts. So you had, even throughout the entire middle school, a regurgitation of elementary school mathematics. So we tried in UCSMP to introduce a new paradigm into US mathematics. No longer did you have to be classified as gifted to take a full course in algebra in the 8th grade. 8th graders at grade level should be studying algebra. This was the curriculum that we would announce sort of from the beginning of UCSMP until just recently. We've changed it just recently. And notice it's the same. The idea is you put everybody on the same track, but they're not on the same place on that track at the same time. So you're basically not ability grouping, you are simply grouping by when are they ready to take this course, assuming that everybody can take it at some time. And notice that there are 2 courses after advanced algebra. One called Function Statistics and Trigonometry, the other called Pre-Calculus and Discrete Mathematics. It's not that there wasn't statistics and discrete mathematics in the earlier courses, it's just this was also a time to concentrate more on those things. 25 years later, how has it changed? It's changed. Now I'm giving you a pre-K to grade 12. This is the introduction you are seeing for the first time. It's our new K. This is with everyday mathematics, which is, as you probably know, a UCSMP curriculum, and starts with pre-K and goes through grade 12. And at grade 6, we now have a new course for the secondary curriculum, which is called pre-transition mathematics. And the idea is, if you're in a K-6 school, you're going to use everyday mathematics because you don't want to have to move into a different kind of structure. And if you're in a 6-8 middle school, you use the pre-transition mathematics. And if you're not in either one of those, you are lost. And no, you have a choice. And so. Now, 25 years later, we can see that this new view about the normal grade level for the first year of algebra has slowly but increasingly been accepted in school districts. From the 13% of 8th grade classes that was in the second international study, that's right here, it's gone up. Now all of this other data are from NAEP, and they're all the same kind of data, so they're very consistent. And look at this consistent increase from 13 to 16 to 20, and not just 25, but in 2000 they had to introduce geometry and advanced algebra. It was now enough people, enough students taking geometry and advanced algebra to warrant moving them from other, on this side, to geometry and advanced algebra. I don't know how many of the other, probably 1% or something like this over here, and moved to 3, 5, and now 7% of students are taking geometry and advanced algebra in 8th grade. That's now the honors. That's now basically the big honors track. Because of the increased percent of students in 8th grade algebra, the amount of mathematics taken by high school students has also increased dramatically. The National Center for Education Statistics studies the transcripts of 10% of the nation's high school graduates chosen randomly, and they do this every few years. Now they're starting to do it every 4 years. And I might say they did do it in 2008, but as far as I know, I could not find that the data has been yet released. Now, if you look at this, you see the transcript studies say that a kind of algebra with trig course, that's this, an algebra with trig or a course beyond second year algebra, not a review second year algebra. You know what I mean by a review second year algebra. A review second year algebra starts out with linear equations and then does systems of equations, and then does, by the end of by around March, you may get to exponential functions. That's a review. That's not what we're talking about. We're talking about a solid advanced algebra with trig or something like that. But look at this. Only 10.7% were in pre-calculus or calculus in 1982. 10.7. And what was it in 2004? On the transcript, this means they completed it. 33%. A tripling of the number of students in pre-calculus or calculus. That means a tripling of the number of students who took 4 years of high school mathematics at least. You're with me? That is incredible, folks. This is a paradigm shift of who's taking it, not just the people going into science and engineering or your brilliant students. This is a paradigm shift, and I might say it's more than 33% in 2008. We can predict it. look at this trend, there's still ways to go. Here's another, and my more favorite rendering of some of the same data and more, because this is also from the National Center for Education Statistics. Here we see the 1982 and 2004 data at the top and the bottom, and the 1992 data in the middle. Here is the 10.7%. It's in the dark and striped squares. Here's the 33% here. Okay, do you see how that? You see, and now we're seeing where everybody else got. How far did all the students get? If you compare now the 2004 students with their counterparts in 1982 by extending vertical lines upward. So you say, okay, let's look at the students who are in our 4th year of high school mathematics. They finish with the 4th year. Where were those kinds of students in 1982? And what you find is those kind of students, none of them were taking the pre-calculus course. Those kinds of students. They were all either in a kind of algebra with, ended with an algebra 3 course, or they ended with an algebra 2 course that's sort of a basic kind of algebra 2 course. So when an experienced teacher who's teaching 12th grade mathematics says, I'm teaching my students, they're not the same as they used to be. The teacher's absolutely right. They are not the same. Half of the students that teacher is teaching are students who would not have been in that population 25 years ago. So we're getting a new group of students in advanced mathematics who need more time to learn mathematics. It's not the same kind of student. Those who cling to the old paradigm that 8th grade algebra is meant only for honor students only often argue that students who take algebra in 8th grade drop out. You know, once they've taken their math, they drop out. Well, let's look at this. This is from the high school transcript study, but now from NAEP, the 2005 graduates. And those students who entered 9th grade with less than algebra, if they entered those students who took less than algebra in 9th grade, they took a pre-algebra general math course, very unlikely to go beyond algebra 2. They're very unlikely, as you can understand, because they would have to somehow double up, right? If they didn't take algebra 1 in 9th grade, they'd have to double up. If they took algebra 1 in 9th grade, 57% of this cohort, that's the mode, took algebra 1 in 9th grade, then how many stopped at geometry? 15% of them stopped at geometry, 47% stopped at algebra 2, and 34% took more. This is your standard 9th grade. This is how much the typical kid took. If they took algebra before 9th grade and they had geometry or algebra 2 in 9th grade, 83% took more than algebra 2. They're going on. And in fact, it's 83% of those who started with geometry. It's not even reported those who started with more, because it was just assumed that everybody took all of the mathematics they could. And it's not just true in mathematics. The number of credits earned in core subjects by high school graduates has gone up in all disciplines. From 1990 to 2005, in English it went up 2/10 of a course. On the average, in social studies, over a half a year more of social studies in 2005 than 1990. In math, over a half a year more. And in science, over a half a year more. Their students are taking more academic subjects in the last 15 years than they ever have done before. We are, despite our love of mathematics, there are those other courses. What can you do? By increasing the number of students who take algebra in 8th grade, we've dramatically increased the number of students who take calculus in 12th grade. From 2000 to 2008, the number of A-B calculus exams increased 64%, and the number of BC calculus exams has increased 88%. I put the number for 2008 in italics here because I have imputed these numbers from the public school numbers that have been posted. The totals have not yet been posted, I think, for all schools. The other numbers are for all schools. And well, they are all for all schools, but these are not the numbers that were presented. What's interesting to me is about 79% of the students who take the A-B test are public school students. 79%. 80% of the students who take the BC test are public school students. I'm just surprised by that. I would think that it would have been, the private schools would have more students taking the BC than that. Okay, this graphic is more dramatic about the calculus exams. This is a slide from David Brassoud, the president of the Mathematical Association of America. And you will notice here that it compares the enrollments of calculus students in 2-year and 4-year colleges with the number of students who take one of the AP calculus exams. In 2006, that's the right data point, the 3 right data points. For the first time, the number of students taking the AP exams, which is only half the number taking the AP courses, the number of students taking the AP exams was greater in high school than the number of total number of students taking calculus in college. Got that, folks? More students are taking calculus in high school than are taking calculus in college. It's no longer a first-year college course. You could argue it is now a 12th grade course for students. It's then somewhat amazing. Oh, and it's the brown, the curve that looks exponential, that's the rise in the AP. You see, it wasn't that way even 10 years ago, but it is that way now. What's surprising is that the grades on the AP calculus exams have not declined. I don't have the grades for 2008, but I have the grades for the last 4 years before that, and the mean grade on the AB exam went from, 2.97 to 2.94, but you can look and you can see that the grades of 5 are fairly consistent, grades of 4, 3, 2, 1, and many people in this room, I'm sure, have been, or some people, have been calculus exam graders, and you know the College Board makes a real attempt to make the grades 1 year equivalent to, mean the same thing as the grades another year. So it's not as if they have this curved. It's not curved. It may have originally been curved, but it's not curved in general. It's not like we need 20% 5s or something like that. Even the BC test, it's actually gone up. The mean on score in the BC test has gone from 3.65 to 3.71 in those 4 years. And during those 4 years, there was a major growth in the number of students taking the test. So you can see what's happened. We have increased our yield without decreasing the quality. That is really something. Do you see that in the newspapers? You ever seen that? You haven't seen one article on that? Even page N, and even page N+1, where there are only N pages in the newspaper? The 8th grade students who take AP Calculus overwhelmingly are steered from that course, from 8th grade on. Of course, they're better students. They're good at math, they tend to be motivated, they don't need applications of mathematics to pique their interest, but they need a broad curriculum as much as any other students. They need statistics and mathematical modeling. In fact, you could argue these students need these subjects at least as much as other students, because even if they don't major in mathematics, and only 1% of our students are majoring in mathematics, so most of these students are not majoring in mathematics, they're likely to go into fields that use mathematics. So 4 years is enough for our best students if we're willing to let them leave high school with a narrow mathematics education. There's no question we have really been successful with our best students. But then what do we sacrifice? We sacrifice, usually they have a little or no statistics, very little applied mathematics. I might say that about 100,000 students took the AP statistics test. That's growing and growing also, just like the AP calculus test. The number who took it's about 36% of the number who take the calculus test. About a third take the AP statistics. And the grade distributions have been staying the same, again, in the statistics, just the same way as they've been staying the same in the calculus. But let me move on now to discuss our students who are not the best. There are a large number of students, about 2/3 of those who take algebra in 8th grade, who don't take AP exams in 12th grade. They may take calculus, but they don't take the AP exams. They may not take calculus. The increasing number of students who take algebra in 8th grade and don't take AP require at least 4 years of mathematics between algebra and calculus. This is my argument for them. They need more time. And I'd like to talk about why they need 5 years or even more, and why they need 5 years or more and the other students 4 years. I'd like to go beyond the fact that some students are simply smarter than others. My kid, always smarter than anybody else. Any parent, right? My kid. If we can double or triple the numbers of students in classes that we used to think were just for the gifted, we can double or triple, and that's what we've done, then we should allow ourselves to wonder whether there are non-cognitive reasons for differing rates of getting through math courses. Now we're, I guess, in a way, getting close to what Katie Haycock was talking about this morning. For purposes of examining these effects, I think it's useful to realize that high school students in the U.S. can roughly be divided into 6 categories. There's the selective school college bound, maybe 10 to 15% of students. There's the non-selective school college bound who will get a bachelor's degree, 15 to 20% in there. The college bound who will not finish college, big number, another about 20%. The workforce technical school bound, 10% maybe, 10, 15. The dropout who gets a GED, which I might say is not counted by certain people as having finished high school. Big policy point of whether you count these people. It's now about 15% of students who get GEDs. And they're not counted by the people who want to tell you that the dropout rates are high. So they're counted as dropouts, even if they get a GED. Very interesting. About 88% or so of students in the United States get either a high school diploma or a GED. It's about 72%, 73% if you don't allow the GED. So it's a big difference. It's half of the students who drop out get GED. And then last, the student who will never attain high school equivalency. About 6. What the preceding analysis has shown is that the selective school college bound can go from algebra to calculus in 4 years. And maybe even the non-selective school college bound, they'll take calculus, and maybe even the non-selective, they can go in 4 years. We know what to do with them. They're so successful, by the way, this first group, that college math departments often never see them. They place out of their college mathematics. They may never take a math course in college. They've changed the character of freshman mathematics courses in 4-year colleges. When math professors in colleges say the students they're seeing are not as well prepared as the students they used to say, you have a combined effect of that high school thing of, yes, there are more students, these are the kinds of students you never saw before, but also you're not seeing the top. The very top have placed out of your courses. The second group is a group of this talk is quite a bit about. They get as far as pre-calculus. They often take no calculus. They often have to take calculus in college, but they typically don't place into calculus. They place into pre-calculus. And here's an example of this. This is CBMS data, the Conference Board of Mathematical Sciences. They collect data every 5 years. And it tells you in 4-year colleges, the number of enrollments, these are in thousands. These are in thousands. I should have put that somewhere. In the entire country, they had only 590 students in calculus in 1980. No. 590,000. Okay, so you can see that the number of calculus students in college, in these 4-year colleges, have remained rather constant, where the pre-calculus has gone up and the pre-college has gone down. Pre-college means really remedial. Most of these places will not think necessarily of pre-calculus as remedial. They'll give credit. They'll give graduation credit for pre-calculus, will not give graduation credit for pre-college. And this means this is pretty successful too. This means we've really done a nice job. And we, of course, have more students who don't take calculus who already have calculus. Let's go on to the college bound who will not finish college, often taking only 3 years of high school mathematics. And more often than not, going into a 2-year college before they go to a 4-year college. Very common. And when we look at the mathematics enrollment in 2-year college, then we see a different thing. You see what we see. We see calculus has, well, it's kind of been reasonably steady. It went up and then back down since 1980. Pre-calculus has gone up. dramatically since 1980, but look at also what's happened with the pre-college, that is what we would call remedial. And that left column has more than doubled since 1980. Students have to take this mathematics. They need to take this mathematics in order to go on to major almost anything. And there you see the people in the two-year colleges saying, look at all these remedial students, look at what we have to do. Those who cite these statistics often want the person who's listening to believe that K-12 mathematics has failed. The reason is either because the curriculum in high school is too weak, the students weren't counseled well enough, didn't take enough math, the teachers were too lenient, the students didn't work hard. That's often the end of the analysis. Blame the curriculum, blame the school, blame the teachers, blame the students. I don't think there's really, those aren't the reasons. There's no blame. Everyone has been working as hard as they can in order to succeed in mathematics. But for these students, for economic reasons, many students cannot or do not feel it worthwhile to devote the time that it takes to learn the math they need to learn in order to be successful. It's for this reason that, particularly for such students, we need to emphasize the utility of mathematics, the ways in which math knowledge can help in financial and other decisions a person makes. Here's my data to support that. Remember the data about the percent of students who had completed pre-calculus or calculus. Remember that there was this percent that had gone from 10%, to 10.7 to 33%, more than tripled, the pre-calc and calc. Notice that in 2004, this is the same 3 years, in 2004, a white student was about twice as likely to complete these courses as a black student, and 3 times as likely as a student of American Indian heritage. Blacks and Hispanics were reasonably similar. Asians were half again as likely as whites to finish these courses. There are large differences, big differences, ethnic differences. But now look at what happens if this data is disaggregated by socioeconomics. The highest quartile is half again as likely to take these courses as the next highest quartile. It's 3 times as likely to take these courses as the lowest quartile. When you have little hope of being able to graduate from college, when you need to work so you can't devote the kind of time that it takes to learn mathematics, you need to work in high school, when you're beaten back by being called dumb, deficient, you name it, just because it's taken you more than 4 years to proceed from algebra to calculus, you lose your desire to learn. And with that, you drop out of mathematics and perhaps out of school entirely. If we were to realize that it's not unnatural to take 5 years to proceed from algebra to calculus, it's done in most other countries because they start algebra earlier, and even more years in some cases because of practical situations, then maybe we would not characterize those students who take longer as remedial or behind, tell them that they have deficits, and lead them to believe that mathematics is beyond them or that what they learned in high school won't help them. Maybe if we were to realize it takes more time, we would be more lenient regarding mathematics prerequisites for courses in other departments. It's interesting that math departments in 4-year colleges often do not wish to offer pre-college courses, the remedial courses, and even regret to offering pre-calculus courses. They really don't want to offer these courses. How different mathematics departments are from foreign language departments, who want students to study languages regardless of how much they knew before, and who don't necessarily care whether a student had studied the language in high school or not. Isn't mathematics somewhat like a foreign language? Let anybody in. The math departments love to go, you can't get in unless, The way we view the time between algebra and calculus is particularly serious because it can be life-altering. A student can be forced to spend another year in college to make up these deficits. This can mean the difference between graduating and not graduating. A student can be kept from majoring in what they want to major in. A student can go into debt or more into debt. The situation is quite different in many other countries where college is as free as high schools are in the United States. I grant that when students have to pay for an education, they take it more seriously, but the U.S. is no longer the country that sends the largest percent of an age cohort to college. We are now quite a bit behind many other countries in Europe and Asia. In sum, we have been very successful at educating a new group of students, 2 and 3 times the size of the group 25 years ago, to a reasonable level of attainment in school mathematics. But we have a ways to go, and it looks as if we're going to have to solve some economic problems before we can hope to continue the positive trends of the past 25 years. What I mean by this is, if I'm a senior or a junior, and now I can work, and I think I have to pay for college, my parents tell me, we'll share the expenses with you, but you've got to come up with some of it. And that's true for quite a large number of students, and I might say it's true this year more than it was last year because of the economic situation. So students have to work. Do you know what is it, a quarter of our seniors work more than 20 or more hours? If you're working that kind of time, you cannot devote the amount of time it takes to learn mathematics and science and that foreign language you're taking and the social studies course and read the stuff for English, all of which people are telling you you need if you're going to be successful in college. You can't do it. You don't have the time. So you do the minimal. You try to do some of the math. You don't really give yourself the kind of... Most of us, I think I'm going to can speak for most of us, when our children, if we had children, when they went through, we viewed school as their job. School is your job. And maybe you have a little job outside, but what comes first is your schoolwork. That isn't the case. What if I have to go home and I have to take care of 3 younger brothers and 2 younger sisters and my grandmother? You know what I'm talking about? Or what happens if I'm pregnant? Oh, not me. Not me. But that's a hypothetical for someone else. But you understand that there are these social situations that are concomitant with poverty, with lack of having, and now it's not just poverty, even being a middle-class parent. One way we may be able to deal with the belief that schooling has failed many of our students is to realize we are asking students to complete a far more complex math curriculum in 4 years than a more select population was asked to complete in 4 years. And we should inculcate the idea that 5 years from algebra to calculus for most students was a good idea then, and it's probably a good idea now. Thank you very much.